All right, good morning, everyone. So, just kind of quick recap what we did yesterday. So we introduced the idea of an electric field. So again, that's denoted by capital E with a vector sign over top of it. So the electric field is defined as the limit as the test charge's charge goes to 0. So that's little q here, where little q is a positive test charge, is times then, or at least the limit of, the force divided by the charge. So again, what the electric field represents then is the force that a particle of charge q would feel at a given point in space. This is then what the electric field represents. So yeah, electric field is a vector field, meaning it has a value at every location in space, as well as a direction, because it's in the direction of the force that that particle would feel at that given point. So we also introduced the idea of electric field lines. So electric field lines are simply a visual representation of what the electric field would look like. Okay? So what we said was that positive charges act as sources of electric fields. So my electric fields have to start off on positive charges and then radiate away from there. Now, in the absence of another charge, electric field lines always move in straight lines. So, negative charges then are sinks of electric fields, which means that electric field lines have to terminate on a negative charge. So if I had only a positive charge in my space, the electric field lines would then terminate actually at spatial infinity, where the electric field magnitude would actually go to 0. Here, for the negative charges, that means the electric field would actually originate at spatial infinity, where it would terminate then on the negative charge. Okay? Now, one thing I didn't point out yesterday, which I'm going to point out today, is typically when we draw these electric field diagrams, the density of the electric field lines represents the strength of the electric field. So the more dense that the electric field lines are, then the stronger the electric field happens to be. Okay? So if you look kind of near the charge, the density of the field lines near the charge versus the density as you get further away is greater near the charge, so the strength of the electric field is actually greater. So for example, if I had, say, one charge here, positive charge, that was represented by 5q, and if I had another that was represented, say, by 3q, then on the 5q, I would just draw more electric field lines. So for example, on the 5q, I might draw 5 lines. So I might want here, 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 and here. So this has a greater density, where the one that has 3q, this one I might only draw 3 lines, since this one has a weaker electric field. So again, the density of the electric field lines typically represents the strength of the electric field. Now, again, this is only for visualization purposes, because in theory, there's actually an infinite number of electric field lines, or regardless how many charges that I have, okay? Because there's an infinite number of different paths that a particle could move. Okay? So again, this is only for illustration purposes. So the last representation we want to look at is what's known as a sheet of charge. And we want to see, what does the electric field look like for a sheet of charge? So here is going to be my sheet of charge. So I'm drawing it in kind of a 3-dimensional sense. So let's say the x-axis is going this way, y-axis is this way, and the z-axis is this way. Now here we're going to specialize, at least for now, into an infinite sheet of charge, which means it extends out to infinity in all directions. So this thing is infinite in length. So this is just a plane. So I have a plane which happens to have a charge on it. Okay? So let's say this plane then has a total charge of, say, capital Q. So I want to know, what does the electric field look like for this sheet of charge? So to do this, we're going to look at actually a side view of it instead. So let's look at the side view of it. Side view. So let's say here's my sheet of charge. I'm going to draw a little bit thick, but typically we're not going to think about its thickness. It's simply going to be a 2-dimensional sheet with no thickness. But for now, I'm going to draw thickness to it. So if this thing has a charge, what I'm going to assume is that that charge is uniformly distributed throughout the entire thing, which means that if I look at every location, each location then is going to have a charge, where the charge of each one of these is going to be exactly the same. So even though the sheet itself has a total charge of capital Q, I'm going to imagine that this thing has uniform charge density throughout the entire thing. So at any location I look at, the charge is exactly the same. So let's for now pretend that this is positively charged. So we know then that the electric field is going to look like what? So from this charge, I'm going to have electric field lines that do something like this. From this one over here, I'm going to have electric field lines that do something like this. And et cetera. Somewhere over here, I'm going to have lines that do this. And et cetera. Okay? Now, what I want to look at then is the superposition of these fields. So basically what's going to happen then is what? Let's say this electric field line here is going to superimpose with this electric field line here, which means that if I was looking at these two, one points down to the left, the other one points down to the right. But since these all have exactly the same amount of charge, what has to be true about the strength of the electric field here versus the strength of the electric field here? They would have to be the same, right? Since the charge is the same, they would all have to be the same. Which means that we have two vectors which point like this, right? One is pointing down this way, one's pointing down this way. So what happens to the horizontal components of those two electric fields? They're going to cancel. They're equal and opposite, which means that the sum of this electric field line here plus this electric field line is simply going to give me one electric field line which points downward. Same thing's true for these up ones. And if I superimpose all of these charges across, what will happen is that every single horizontal component from all of these electric fields are all simply going to cancel each other. Which means the total electric field for this particular charge configuration only points vertically. So it turns out that for an infinite sheet of charge, the electric field points perpendicular to the surface. So these are all at 90 degrees to the surface. So this is the electric field. So to go back to my original picture, what that means then is the electric field in this case would point perpendicular to the surface at all locations. So this would be my electric field. And what's actually very, very interesting about this is that it turns out that the electric field magnitude is actually constant. So it turns out that the magnitude of this electric field is actually constant, and it's everywhere given by eta divided by epsilon naught. Actually divided by 2 epsilon naught. Where eta, as we defined before, is equal to the total charge divided by the total area. So this is the surface charge density. So it actually turns out that it doesn't matter how high I am above this sheet, or if I switch to the other version of the sheet, it doesn't matter where I am relative to the distance away from the sheet, the value of the electric field is exactly the same. So whether I'm this distance, say 1 meter away from the sheet, or if I'm 2 meters away from the sheet, the value of the electric field actually turns out to be exactly constant, which only depends on the charge density divided by twice of epsilon naught. We'll derive this later when we get to Gauss's law. Okay. We'll see where this actually comes from. But the point is, if I have a sheet, the value of the electric field is simply equal to a constant. So what happens if I put two of these sheets next to each other? So let's say I have one sheet of charge here, which has a total charge of Q, and I put a second charge sheet here, which has a total charge of negative Q. What happens in this case? Well, here we know this is positively charged, so the electric field from this one has to point radially away from it, or perpendicular to the surface at all locations. The bottom one is negatively charged, which means the electric field has to point in towards it from all directions, perpendicular to that surface. So for funsies, let me extend one of these guys out in this direction, and I'm going to extend this one down into this direction. So we can actually see what's happening. So what will happen then is what? If I'm looking up here outside of this electric field, what happens then is I have this electric field from the top one pointing away, but I have the one from the bottom one which is pointing towards. But since they have exactly the same magnitude of charge, what I know then is that the blue electric field line has exactly the same magnitude as the red electric field line. They're just in opposite directions. Which means that if I sum two vectors equal magnitude in opposite directions, what do I get? I get 0, right? Which means that for this configuration, the total electric field on the outside here is simply equal to 0. What about down here? Well, down here, now my red line is going downward, the blue line is going upward, but again, since this charge magnitude is the same as that charge magnitude, that means this electric field line is the same as this electric field line, which means, again, they're equal and opposite, which means the electric field out here is also equal to 0. On the inside, What's happening now, though, is what? This electric field line points down. This blue electric field line points down. They're actually in the same direction in between, which means that the total electric field on the inside is not 0, but it's actually equal to epsilon eta divided by epsilon naught. So what this tells me then is if I have two sheets of charge separated by some spatial distance, the total electric field on the outside is 0. Total electric field on the outside is 0. The only electric field which exists is in between the two plates, where in that case, it's just the charge density of one of the plates divided by epsilon naught. This is the total electric field. This is a configuration that's going to come back and haunt us a lot. This is what's known as a parallel plate capacitor. We shall see this often. Okay? So just bringing it up now so we know exactly what it looks like by the time we get back there again. Dylan. Correct, that's because I have two components of the electric field. That's right. So if I wrote this out, switch back the other direction. So this is equal to epsilon over, eta over 2 epsilon naught plus eta over 2 epsilon naught, which then gives me the eta over epsilon naught. Because I have two components. This one has the same magnitude as this one, so I just summed the two together. Nathaniel.
What did you say eta represented?
So eta is the total charge divided by the area. So this is what we call the surface charge area. So all that means is this is the amount of charge I would have if I grabbed an area here. Okay. So it just means if I know the area which I'm looking back, so let me go back to my original picture. So if I was looking at this area here, that represents the amount of charge enclosed in that area. So this is what we call eta. So eta then is the charge enclosed inside of some area. And again, we mostly do that because if this thing has a total charge of Q, but it has infinite in extent, then the total area is actually infinite. So if I take Q divided by the total area of infinite, that's 0. So typically this thing, eta, then is going to have units of coulombs per meter squared. So I'm going to say, this thing has a surface charge density of, I don't know, say 2 microcoulombs per meter squared. So that means every meter squared, it has exactly 2 coulombs or 2 microcoulombs worth of charge. Okay. That's what that means. Okay. So again, electric field lines. These are only a visual representation of the electric field. So we can get an idea of what the electric field looks like. But again, they're not quite set in stone. It's mostly just there for visualization purposes. So the question then becomes, how do we actually calculate an electric field? So let's look at the electric field of a charged particle. As our configurations get more complicated, we then have to do more complicated things. Let's look at a point charge. So what we know is that the force between 2 point charges, so let's say I have one charge here which has a total charge of Q, and then here is going to be my test charge of little q. Now we know Coulomb's law says that the electric force is then equal to the electric constant times charge 1, which is big Q, times the second charge, which is little q, divided by the distance r squared, where the distance r, again, is the center-to-center distance between the two. And in this case, this is going to point in the radial direction. This force is going to be pushing out this way. This is the direction of my force. So I'm calling this direction the r hat, or the radial direction. Now we now know, though, is that the electric field then is equal to simply the force per unit charge, which means here, this is going to be equal to k times q divided by q times r squared in the r hat direction, which means that this q cancels with this q. So this is then going to be k times q divided by r squared in the r hat direction. This is then the electric field of a point charge. So this says if I have a single point charge, the electric field at that given point simply depends on the magnitude of the charge of the charge, the radial distance I am away from that charge, and then r just represents the direction. So what that means then is what? Anywhere along the circle, and this has a circle of radius of r. The magnitude of the electric field is constant everywhere across this circle, but the direction is going to change because it's going to be the radial direction. So anywhere along the circle of radius r, the magnitude of the electric field is simply equal to constant, but the direction will always be in the radial direction. So if my particle was sitting here, electric field would be this direction. If it was sitting here, it would be in this direction. If it was sitting here, it would be in this direction. So this is the electric field. So the electric field points radial away from a positive charge, and its magnitude is given by the distance m away from that charge. Now, if I had a negative charge, the only thing that would be different would be that what? This Q would be negative instead, which means it would point in the negative radial direction. So it would point inward instead of outward. That's it. So this is the electric field of a point charge. Now, because the force between two point charges abides by the superposition principle, that means the electric fields do as well. So remember, if we were looking at the force on the third particle by all of the other charges, I'll write this as j not equal to 3 of F3j, if I simply divide both sides of this by q, what this means then is that the electric field from the third particle then is equal to the sum over j times then E j. So basically, all this means then is that the total electric field at some given point is then simply equal to the sum over all of the electric fields. Let me write it this way. Which means that since the force abides by the superposition principle, so does the electric field. Electric field abides by the superposition principle. Everybody's okay? Not too bad, right? So let's use this. Let's do some examples. So the first example says, let's refer back to that first problem that we did with electric forces. So we have this charge configuration where, again, we have Q1 sitting here, negative 86 microcoulombs, Q2, 50 microcoulombs. But now we're going to pretend that Q3 is not here. Okay. What I want to know then is what is the value of the electric field at this point, which we're going to call point A, which is the point where Q3 used to be living. So let's draw it. So all this means is, so here's my x-axis, my y-axis. Here's Q2. Here is Q1. What I want to know then is at this point here, I'm going to call it point A. What is the value of the electric field at point A? So what is the value of the electric field? Let's plug in a number. So this is minus 86 microcoulombs. This was 50 microcoulombs. This distance was 30. This distance was 52. This distance was 60. And this was the angle theta, which was equal to 30 degrees. Centimeters, centimeters, centimeters. So again, all I want to know then is what is the value of the electric field at point A, which is where Q3 used to be. So good. So now what we know is what? The total electric field at point A is simply going to be the electric field from charge 1 plus the electric field from charge 2, vector sum together. That's all this means. So again, since I have two charges, what that means then is the total electric field here is going to be the charge, or the electric field from this guy plus the electric field from this guy, vector sum together. So the superposition principle. So good. So let's draw our electric field lines first. So first off, we know that what? Q1 is a negative charge, which means that the electric field has to point downward towards Q1 along the line connecting that to point A, which means our electric field then has to point in this direction. So this is going to be E1. Okay? Our electric fields point towards negative charges. Q2 is a positive charge, which means that the electric field from Q2 has to point radially away from Q2, which means at point A, this guy's going to be pointing upward. So E2 is going to point this way. The total electric field then is the superposition or the vector sum of those two, which means this is going to be my total electric field at point A. So good. So what this means then is that the electric field at A is going to be equal to what? The electric field from 1 plus the electric field from 2. Now again, here we can see that E1 is actually two-dimensional, where E2 is actually one-dimensional, so we can break this guy up into components. So we're going to do what we did last time. I'm going to move my coordinate system to here. So I'm going to call this my x-axis, this my y-axis, meaning that this is the angle 30 degrees. So that's the same angle as before. Good. So we're going to write this then as E1. So this is going to be E1 times cosine of theta in the I-hat direction, minus then E2 times sine of theta in the j-hat direction, plus then E2 magnitude, which only points in the j-hat direction. Okay? Now from here, we're simply going to use our new friend. So we're going to say that EA is then going to be equal to, so let's put these guys together. So this is going to be E1 cosine of theta in the I-hat direction, plus E2 minus E1 sine of theta, all in the j-hat direction. Okay. So, good, from here, we know that E1 is simply going to be equal to K times Q1 divided by the distance R1 squared times cosine of theta in the I-hat direction, plus K, I'm going to go ahead and factor that out. So I'm going to get a Q2, let me put absolute values around these, divided by R2 squared minus Q1 magnitude divided by R1 squared times sine of the angle all in the j-hat direction. Okay? So let me go back and just clarify what some things are. So that means this distance of 60, this is going to be R1. This distance of 30 then is going to be equal to R2. Those are those distances. Everything's okay? Not too bad, right? So plugging our numbers, what we find then is that this is equal to 1.86 times 10 to the positive 6 newtons per coulomb in the I-hat direction, plus 3.93 times 10 to the 6th newtons per coulomb in the j-hat direction. So this is our total electric field at this point. It's okay? Now, there was actually a quicker way we could have done this. I'll point that out now. The quicker way we could have done that was actually to use the result of the force that we knew before. Right? Because when we did this before, we found the force in unit vector notation. But remember that the electric field is the force per unit charge, where in this case, the unit charge would be that of Q3. So another way we can verify that this is correct is we could have found the electric field at point A as being then the force that we found before from 3 divided by the charge Q3. It would give us exactly the same result. But here we're assuming we didn't do that before. That's what we did. It was okay? Let's do another example. So the next example says that this was 5, let's go to 6. In this figure, we have 4 charges. We have Q1, Q2, Q3, and Q4, where D here is the distance of 5 micrometers, so 5 micrometers, where Q1 and Q2 are both the same, so they're equal to 5 times E, where again, E is the fundamental charge. Q3 is 3 times E, and Q4 then is negative 12E. And I want to know, what is the magnitude of the electric field at point P, where point P is the origin here, so this point here. So I want to know, what is the value of the electric field at that point based off of this charge configuration. Okay? So let's do this. Let me draw that picture. So I have charge here, here, so this is Q1, Q2, here, Q3, here, Q4, and I know this is distance D, 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 and D, where D was equal to 5 micrometers, and then Q1 was equal to Q2, which was equal to 5E, Q3 was equal to 3E, and Q4 was equal to minus 12E. You get those right? Molly said, I'm taking your word for it. Everyone's okay? So good. What we want to know is what is the total electric field at this point, at point P. So we want to know what is the total electric field at point P. That's what we want. Now, to do a problem like this, the first thing we should always do is not math. The first thing we should always do is look for what's called symmetry. What I mean by that is we're going to try to identify, by looking at it, are there any things which are going to cancel based on the fact that they are symmetrically placed, they have the same charges, same distances, things like that. Because if I don't have to do a calculation, I'm not going to do it. I'm going to be lazy. I like being lazy, but I like being lazy in a smart way. Right? So that's why we make machines, right? That's why you guys exist in engineering. We make them to be lazy. That's the point. So here, we're going to first identify, is there anything that's going to cancel that I don't have to calculate? So is there anything that in this picture will automatically cancel, and I know that the electric field from that contribution will give me nothing? So what do you think? So is there anything in this picture that will automatically cancel?
Is it Q1 and Q2?
Q1 and Q2, exactly. So what I know is that Q1 and Q2 have exactly the same magnitude of charge. I know they're exactly the same distance away from the charge, or from the point of interest, point P, and they're along the same line connected, which means that since this is a positive charge, the electric field for him points this way. This is a positive charge, which means his electric field points this way. Those two electric fields are equal and opposite, they automatically cancel. Which means I don't care about them. They might as well not exist. They give me nothing. Right? Now, since I know those two don't exist, what does that tell me has to be the direction of the total electric field? Well, the total electric field then has to be along the line of these two charges. Because if this one's a positive charge, I know the electric field from him has to point down in this direction, since it points away. That one up there is a negative charge, so I know this one has to point in this direction because it points towards it. Which means the only direction that the electric field can point is along this line that is connecting these two particles. Which means that instead of working with this tilted picture, I'm going to go ahead and rotate it. Because I can. So instead of doing this picture, I'm instead now just going to switch it so that this is Q4, this is Q3, and this is point P. Why work with components when I don't have to? I can arbitrarily call anything the axis I want to. So I'm going to simply call this guy my y-axis. Great. Remember, one of the first things we learned in 205, you can rotate your coordinate system to anything that you want to. Make it as easy as possible. So here, since Q2 and Q1 canceled, let's just make it this way. So good. So what I know here is that Q3 is a positive charge. So I know in this case, the electric field has to point down this way. Right? It has to point radially away from it. Q4 is a negative charge, which means the electric field has to point towards it. So its electric field has to point this way. So this is going to be E4. So that means that my total electric field at point P is simply going to be the electric field from 4 minus the electric field from 3. Okay? So this then is going to be equal to what? K times the magnitude of Q4 divided by, let me call that R4 squared, minus K times the magnitude of Q3 divided by R3 squared. And technically, this is all in the y direction. Good. Now, the other thing I know is this K here is the same as this K, so I'm going to go ahead and factor that out. What I also know is that R4 here is simply 2 times D away, right? Because this is D, so that's 2D away, where R3 is simply then equal to D. Right? So let's factor all that out. So this is going to become E and P is going to be K divided by D squared times magnitude of Q4 divided by 4 minus magnitude of Q3 divided by 1, all in the j hat direction. Okay? You see what I did there? So again, here I'm using R3 is equal to D, R4 is equal to 2D, which means R3 squared is equal to D squared, and then R4 squared is equal to 4D squared. It was okay? So now let's put in our numbers. So what we know is that what? Q4 was 12, so what's 12 divided by 4? 3, good. Q3 was what? 3. So I have 3 minus 3, but what's 3 minus 3? 0. So the total electric field at point P is simply 0. Nice and easy. Always okay? Not too bad. Let's do another one. So the next one then says, so 6 or 7. So this says we have two particles fixed on the x-axis. The first particle is Q1 is equal to 8Q at the origin. The second one is Q2 is equal to negative 3Q at location x is equal to L to the right of the origin. At what point other than spatial infinity is the net electric field equal to 0? So we actually already kind of did this before, but when we did forces, but let's do it again. So again, here is my x-axis and my y-axis. Q1, I'm told, was here, and that was what, 8Q. Q2, I'm told, was here, was equal to minus something, 3Q. So minus 3Q, and I know this distance here is, again, the distance L. So, just to get more practice, we're going to go through the same thing we did before. So again, the first thing we have to do is determine at what point, either in region 1, region 2, or region 3, is it possible to put two electric fields such that the sum between the two is equal to 0. So, same thing as before. So we want to look here, region 1, here, region 2, here, region 3, and determine where in 1, 2, or 3 would it be possible for these two charges to create a net electric field of 0. This is what we want to know. Good. So first question, could we put it in region 1? What do you think? Could we put it in region 1? Dylan, you were quick to react, so what do you think? Oh, so this one has nothing to do with another charge. So this is just, we have those two charges, and we want to know where's the net electric field equal to 0. So here we're not looking at forces, but we're looking at directions of electric fields. So what do you think? So could it be region number 1, where the net electric field between Q1 and Q2 be equal to 0? So what do you think? So is it possible for that to happen based on the magnitudes of these charges and the distances? And it's, I'll make a comment about the one we did before. But what do you think? Who wants to be brave? Derek, you're gonna be brave. What do you think? No, good. Answer is no. Reason for that is, so again, let's draw our electric field lines. So we know that this is a positive charge. So if I was looking at some point here, so let's say this is my point P. So this is a positive charge, so we know the electric field would have to point in this direction, so it has to point away from it. This one is a negative charge, so this one has to point towards it. So this one, E2, would have to point this way. So far so good. And they can be opposite from each other, but the question is, can they be equal? Well, as Derek is shaking his head, no. The reason for that is what? This has a much larger charge than this one does. And again, the distance from here to here is much shorter than the distance from here to here, which means I take a large magnitude, divide by a short distance, that gives me a large number. If I take a small numerator, divide by a large distance, that gives me a much smaller number, which means that no. Anywhere in this region, the overall net electric field will always be pointing this way. So the total electric field will always point in this direction, in this region. The answer is no. We have to think about proportionalities. What about region 2? Could we have a total electric field in region 2 equal to 0? Go ahead, Jared. No, also no, good. Why? Well, same reason. This one is, let's say we're looking at this point. This is a positive charge, so we know the electric field from him has to point this way. This one is a negative charge, which means the electric field from him has to point in exactly the same direction, which means anywhere in this region, the total electric field has to be pointing inward towards Q2. The answer is no. So this region is a no. This region is a no. So the only place it could be possible is, let me do it in yellow, somewhere out here. Because here, what'll happen then is what? This is a positive charge, so we know E1 has to point in this direction. This is a negative charge, so it has to point inward. So again, they can be opposites. But same thing as we had before, what happens now is this distance is much greater than this distance, which means even though this has a small numerator, it's now going to have a small denominator, which means it could be a big number. This has a large denominator, or sorry, large numerator and large denominator, which means that the proportionalities can work out. So this is the only place it can exist. So let's call this distance from here to that place the distance x. So good. So what this means then is that the total electric field at point P is then equal to 0, which is then going to be equal to E1 minus then E2. Because again, E1 here is pointing in the positive x direction, E2 is pointing in the negative x direction. So using this, we can write this as K, magnitude of Q1. I call that little Q1. Little one, there we go, divided by the distance. So the distance in this case from here to here is going to be the distance L, or actually, sorry, distance x. So this is distance x squared. Minus K times the magnitude of Q2 divided by this distance. So this is the distance x, this is the distance L, and this distance is x minus L. So this is going to be x minus L squared. Now, since this is equal to 0, we don't care about K. K is going to go away. That's going to vanish. So let's cross multiply. So finally, what we get then is that magnitude of Q1 divided by x squared then is equal to magnitude of Q2 divided by x minus L quantity squared. Do the same thing as before. Let's take a square root just to get rid of that squared. So now we have the square root. Magnitude of Q1 divided by x is equal to square root magnitude of Q2 divided by x minus L. Cross multiply and then simplify. We finally get then that x is equal to the square root of, I can do bad math in my head, Q1 divided by the square root of magnitude of Q1 minus the square root of magnitude of Q2, all times L. Look at our numbers. What we find in this case then is this works out to be about 2.72 times the length. So this is the only place that we could have the total electric field equal to 0. Now what this also means, which is something I didn't point out when we did this problem the first time, is that since the total electric field is equal to 0, that means the total force on any other charged particle I put there will be 0. Irrespective of the size of that charge and the sign of that charge. Right? So that means is, if I go back to our picture, if this is the point where the total electric field is equal to 0, if I took another charge, let's say Q3, and I put that charge here, that force on that particle will be equal to 0. Irrespective of the size of that charge. That charge could be 8Q, 12Q, 150Q, a million Q. Could also be negative. Could be negative 8, negative 50, negative infinite Q. It doesn't matter. The amount of force is still going to be 0 irrespective of the size of that charge that I put there, because the total electric field is equal to 0. Okay? How much time do I have? Okay, oh, about 10 minutes. Okay. Let's do another example. So this one says that we have these three charges. We have Q1, Q2, and Q3, where Q1 and Q2 have the same charge. That is a fundamental charge. So this is an electron, well, actually a proton and a proton. And then here, this one has another charge of twice of that. So this could be what, an alpha particle. 14. Okay. This distance here is the same as this distance here. So these are 6 micrometers. So what I want to know is what is the magnitude and the direction of the net electric field at point P due to these particles, where point P is this point here. So this is halfway through the line that connects these two, and then this line here. Now again, let's use the idea of symmetry here again. Again, first thing we should look at whenever we do a problem like this is there some sort of symmetry? Can things cancel out without me having to do any calculations? Okay. So the question is, does that happen here? Is there anything that automatically cancels with something else that will give me 0? So I don't have to do any calculations. What do you think? Dylan's shaking his head. Good. What's going to cancel, Dylan? Q1 and Q2. So I know Q1 and Q2 have equal charges. They're also equal distances, and that point is along the line that actually connects the two of those. Which again means that the electric field from Q1 is going to point this way. Electric field from Q2 is going to point this way. Those two will be equal and opposite, so automatically they're going to cancel. So just like before, these two are going to cancel, so the only electric field contribution at this point is from Q3. That's it. That's all I care about. The only thing I care about is Q3. So that means when I actually redraw my picture, if I stayed with that actual coordinate system, the only thing I have to draw is Q3. That's it. And then my point P is right here. Which means I actually already know the direction of the electric field. The direction of the electric field has to be in this direction, because that's the point away from that particle. And I already know what this angle is because that made a square, which means that this angle here is simply 45 degrees. Okay. So I know the direction is that theta E is equal to 45 degrees. I already know that part. So last thing is I just want to know what is the magnitude. So the magnitude of the electric field at that point is simply then going to be equal to, well, simply the electric field from Q3. That's it. So this is then going to be equal to what, K times the magnitude of Q3 divided by the distance R squared, where this is the distance R. Okay? Now the only thing I have to do now is determine what is R. Well, I also know that if I continue this line here, this distance is D, which means if I continue this guy over here, this distance is D, which means this total distance then is going to be what? Square root of 2 times D, which means R is going to be equal to 1/2 of the square root of 2 times D. Molly shook her head like I have no idea what she was doing. Okay, so is everyone okay with this? No, good. Let's draw a picture. So here what I'm going to do is I'm going to draw a square. Okay. So I know this is D, 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 and I'm going to draw a bisecting line here. Okay. And my point P is right here, halfway through that bisecting line. Which means I'm drawing a right triangle. So here's my right triangle. So if this side is D, this side is D, how long is this distance here? Well, Pythagorean Theorem says that this distance is going to be equal to the square root of this side squared plus this side squared. Well, that's the same thing as what? The square root of 2 times D. So this total distance across here is square root of 2 times D. But point P is halfway through that, which means this distance here is half of this distance. So that's the square root of 2 divided by 2 times D. Okay? Loving our geometry? Okay. So good. So let's go back. So now this is essentially going to be equal to what? 4 times K. Actually, no, it's not 4. So if I square this, actually going to be 2k magnitude of Q3 divided by d squared. Plug in our numbers, we find in this case then is that magnitude is equal to 160.2 newtons per coulomb. Okay. So we got one more example. I don't think we're going to be able to finish it, but we can actually at least set it up. So this one says we have two particles, each of positive charge q, are fixed in place on the y-axis where one is at a distance d from the origin, and the other one is at a distance of negative d from the origin. So it wants us to write an expression that gives the magnitude of the net electric field at points along the x-axis, graph that guy, and then determine the value of x that gives the minimum value of the electric field and the maximum value of the electric field. So let's draw the picture. So this is saying is, here's my y-axis, here's my x-axis. I have one charge here of charge q, second charge here of charge q, where this distance is d, this distance is d, okay? Now, what we want to do is choose some random point on the x-axis. This is my random point on the x-axis, call that point P, so that this distance here is the distance x. So the first thing we want to do is determine an expression for the total electric field at point P. Okay, this is what we want to know. That's the first thing we want to know. So first thing we're going to do is go ahead and draw electric field lines. So we know that what? This distance from here is going to be the distance r. This distance from here is also the distance r, which means from this point down here, the electric field points this way. So let's call that E bottom. From this one, it's going to point in this direction, so that's going to be E top. Where this angle theta here is the same as this angle theta here. Now, what's the first thing we notice? So the total electric field at point P is simply the sum of this electric field from the top plus the electric field from the bottom. Well, what's true about the charges from the top and the bottom? They're the same. What's true about the distances to that point from the top and the bottom? They're the same. So what should happen then to the vertical components of the sum of these two vectors? They go to 0, right? Which means that the total electric field then is only going to point along the x-axis. This is it. Does this look scary, similar? This is your group assignment from last time, right? We're just doing electric fields instead of forces. So good. So this says then that's what? The total electric field at point P is then going to be equal to the cosine portion of the field from the bottom plus the cosine portion from the field from the top. But what we know is that the cosine portion of the bottom magnitude is exactly the same as the cosine portion of the top magnitude. So this is simply then equal to twice of the cosine portion from, say, the bottom. They're the same. Good. Now what we know is that this is going to be equal to k times q divided by the distance r squared times then cosine of the angle. So r, we know by Pythagorean theorem, is going to be d squared plus x squared. Cosine, we're going to do what we did for the group assignment. We're going to say we're going to use this angle here, which means that the adjacent side to this is x divided by the hypotenuse, which is simply r. So here we know r squared is equal to x squared plus d squared, and we know cosine of theta is equal to x divided by r. Okay? So finally, we can put everything together. So this says that the electric field at point P is going to be twice of k times q times x divided by x squared plus d squared to the 3 halves. This is my total electric field. So this is my electric field as a function of position anywhere along that x-axis. This was what? Part A. Okay? What's up? Oh, yeah. No problem. I think I'm just going to stop here. We'll have to do the rest next time because I only got like seconds left. So. I mean, I could keep going all day. I don't think you guys want to. So, soon, so we'll finish this up on Monday, and then we're going to start the most fun part, which is continuous charge distributions, which means we're going to spend a whole bunch of time doing integrals. So be ready to do some calculus on Monday, right? We're going to be doing integration by parts, and, well, we're not actually going to do that in class, but we'll definitely be doing U substitutions. Anything that's harder than U sub, I'll forego that to look it up in a table. That will be great. Okay. But we're doing a lot of calculus on Monday. That will be great. Turn this off.